All right, good evening from Boston. Tonight we're going to go over Chapter 8, Geologic Time. This by far can be one of the most difficult topics for students to grasp, simply because it's difficult to understand the sheer amount of time we're actually discussing. For example, the average human being is going to live for about 100 years, okay, give or take a few years. That seems like a long time until you get to a certain age, and it seems like that's a short time. Our country's only been around for more or less now closing in on 243, 245 years, somewhere in that ballpark. Again, to us, that seems like a long time. Human history, depending on whose records you go by, written history goes back somewhere between 4,000 and 6,000 years. Human civilization, at least as we recognize it, in terms of governments, cities, and whatnot, that seems to go back about 11, maybe 12,000 years. But the Earth itself is 4.6 billion years old. So that's a much larger number. Now, in part thanks to recent politics and talk of the national debt and the spending on, say, the wall, numbers like billions are becoming more and more commonplace for people to have heard. But conceptually, that amount of time is very difficult to process for a lot of people. You know, think back to when you were a kid and the clock in the classroom, 5 minutes before the end of the day. How slow did that 5 minutes go? Pretty slow, right? Even the hour and a half, 2 hours I drone on in class can seem like an eternity to some of you. Probably does. I don't blame you. But we're going to be talking about time today. Now, we're going to break up time into two parts for geologic time. We're going to talk about relative time and absolute time. Relative time is going to be time in terms of proper order, okay? So let's say I picked one of you at random and gave you the task of ordering everybody in the classroom by age, based solely on what you can see about the person. You think you could do it? You think you could get at least the youngest and the oldest? Maybe get some of it in order? Maybe? What if I gave you pictures on how to make a pizza? Just showing the different steps of making a pizza all mixed up. Could you put those into the proper order? Yeah, you probably could. So that's what relative dating is that's just putting things into the proper order so that they are themselves in the correct sequence that happened. The other side of this is absolute dating. And absolute dating, or numerical dates as it's sometimes referred to, is basically giving an absolute number of years since the event happened. So something happened 4.5 billion years ago. Something happened 64.2 million years ago. Things of that nature. Okay? So first off, we're going to talk about the different keys to relative age dating. Now, we use a number of principles or laws for this, and it really goes back to Charles Lyell, who published a landmark book, Principles of Geology, in the 1800s. But he was following in the footsteps of James Hutton. Hutton came up with a concept one day while sitting basically at a beach eating lunch. As the story goes, basically what was happening is he was sitting there having his lunch, and he looks down at the beach in the water, and he sees sand ripple marks in the sand. Just these gentle ripple marks from the water going back and forth. And he noticed that the rocks he was sitting on had the same ripple marks in them, but they were vertical. And he realized that all you need to explain what we see in the geologic record is enough time. So he came up with this idea that we call the principle or the law of uniformitarianism. And all that really states is the present is the key to the past. The past is the key to the future. Meaning that with enough time, the processes that we see active on the earth today will explain the rocks that we see. And we can use those processes that have occurred to help us forecast what will occur. So this is really one of the major ones, and it's one of the founding principles of geology. So when we look at relative time and we want to figure out how do we put things in order, how do we look at this, we'll give you a few of these principles. The interesting thing is that for a lot of them, you're probably going to say that's common sense. And yeah, it is to some degree. So let's start out. And the first one is the Law of Superposition. And the Law of Superposition was published by a gentleman by the name of Nicholas Steno in roughly 1669. Steno was, like many of the more well-known men of his age, a quote-unquote Renaissance man, meaning he was fluent in a number of things. Steno happened to be a naturalist as well as a clergyman, an astronomer, and a chemist. The idea of superposition is a very simple one, and that is in an undeformed sequence of rocks, especially sedimentary rocks. Okay, certain types of volcanic rocks also, but mainly sedimentary rocks. The oldest rocks are going to be at the bottom, and they get progressively younger as you add layer upon layer. Think of it if you want like a teenager's room. When you go into the teenager's room or a kid's backpack, the oldest stuff is always at the bottom in there. Another one that Steno also proposed was the Law of Original Horizontality. This is basically describing sedimentary rocks. And sedimentary rocks, sediments in general, are going to be deposited horizontally at the point of deposition in general. We can get some definite places where it doesn't hold up as quite true, but they're generally horizontal. So in an undeformed sequence of rocks that are layered, the bottom layer is the oldest, the top layer is the youngest. Okay, like a pizza or a cake, which part came first? You don't exactly have the frosting and then build the cake under it. If you do, make a video of it, post it to YouTube. You'll probably get a lot of hits. Okay. Another one is the principle of cross-cutting relationships. Cross-cutting relationships has to do with how things cut across something else. To use a cake as a metaphor for this, or a simile, imagine a layer cake. Okay? Everybody can imagine a layer cake. Multiple layers of, say, cake, frosting, cake, I don't know, jelly or jam, cake, frosting, ice cream, cake, whatever. Now imagine I take a large Hershey's bar and I push it into the cake. Which came first, the cake or the Hershey's bar? The Hershey's bar did not come first. The Hershey's bar came afterwards because the Hershey's bar cut the cake. The cake had to exist before the Hershey's bar was pushed into it. Okay? So when we look at rock units, any rock unit that cuts across another rock unit has to be younger than the rock unit it's cutting. Okay? Another one is the idea of lateral continuity. This is basically a concept that states that sediments are going to deposit horizontally until they either pinch out, meaning that the deposition ended at that point because it ran out of material, or it met the edge of the basin, some sort of physical edge that stopped the deposition. So we'll see these environments where they either taper off or they come to an abrupt end. Another one is the law of inclusions. Again, getting back to the idea of food, a chocolate chip cookie. You can add all sorts of things to a chocolate chip cookie. What's going to, in this case, something that's included is going to be older than what's including it. Okay? So let's say, for the sake of argument, I'm making up a batch of brownies. I know I said chocolate chip cookie, let's just go with it. I'm making up a batch of brownies. And I take a bunch of cookies, and I mix the cookies. I break up the chocolate chip cookies, and I mix them into the brownie batter. Which is older, the brownie batter or the cookies? Well, the cookies had to exist first before the brownie batter. Okay? So we see this sometimes in sedimentary rocks when you had a basal unit of material that was being weathered, and we have chunks of that rock that have been weathered out at the surface, and then it gets included into the next deposition cycle that occurs. Then there are the unconformities. Unconformities are most easily expressed as missing time. It's time that is missing. What do we mean by missing time? There is no point on the surface of the Earth where all of the geologic record is expressed. Yeah, we have areas where the oldest rocks are billions of years old, the youngest rocks are thousands of years old, but not the entire record is there. There are large chunks of it that are missing. We call these missing time blocks unconformities. These are areas where we are just missing information. Now, when we look at unconformities, they come in three primary types. The first of these is what we call a disconformity. I'm trying to find in your book a pretty nice one for it. I guess I'm going to look at page 185. This is a kind of a graphic here of a disconformity. So here it's showing you all the different layers that should be in the sequence, yet here is what's actually in the sequence. So we see this wedge of material based on fossils that are missing. Okay, so and this is basically a disconformity is a location where either deposition stopped for a while or erosion occurred, but the erosion was flat. So what you end up with is the sedimentary layers under the erosional surface or the non-depositional surface are flat. The layers above it are flat. The surface in between, it can be flat or it can be what we call a paleo surface. A paleo surface is basically, imagine the landscape around you right now in Nogales, and now imagine dumping a whole bunch of sediment on it and filling it up. That would create a paleo surface. So that would be an unconformity. That is a disconformity. The next one is an angular unconformity. Angular unconformities occur when there's been a distortion of the material. We haven't gotten to here yet, but rocks will fold and fracture. They will bend and they will break. So it's possible to end up with a situation where rocks under horizontal rocks are at an angle or even vertical. So if this is the horizontal rocks near the top, you have these rocks that are angled up on the bottom. This could be because the rocks were bent up into a dome shape, cut off by erosion, and then new deposition occurred on top. They could have been block fault mountains. There's a number of different reasons that it could have been, but the fact is that it was. So what we see is that there had to have been a lot of time that was necessary to deform the rocks in the first place, then erode them down, and then cause new deposition to occur. So all we're seeing is we see the results of the erosion, the folding and faulting, and the erosion, but we're not seeing the actual events that happen in between. I know I'm moving all over the screen. It's a little. The seat here is a little low and feels a little funky. So there's that. Then the other one is what we call a nonconformity. A nonconformity is basically the idea that you have much older igneous and or metamorphic rocks that have been weathered down and exposed, and then younger sediments are deposited on top of them. So page 187 kind of goes through a sequence of this. I'm just going to briefly go through it. So you have your deposition, all the layers are deposited, you get some sort of deformation where the material is folded, faulted. We have some igneous material that is intruding into it. Maybe we have some high-grade metamorphism that occurs, or some metamorphism that changes the rocks around it as well. Then that gets eroded down fairly flat, and then we get new sediments on top of that. Okay, and by the way, something similar to that, Grand Canyon. We see things like this in the Grand Canyon. And so those are the three types of unconformities that we can have. Again, they're all missing time. So what do we do with this? Well, what we do with this is something like this. You're going to want to start on page 184, down at the bottom, figure 8-11, to understand this. But when you read this, you're going to kind of go a little backwards. Okay? So what we're doing is basically, this is what we call a block diagram in the book. So it's showing a series of rock layers with the unconformities in there. You can see them. They're not labeled. What they did, though, is they go back. If you go back to page 182, let me pull back for this. They actually go through the whole sequence that they went through to create that block diagram. What we're doing with relative age dating is trying to do the same thing. We're trying to tease out of the block, based on the information that we can see in the block, based on the factors that we know, the principles, the laws, and how they relate to each other. We're trying to see how these things organize. Okay, now there's another principle I want to talk about. Excuse me. Before we get to it, too far into it, when it comes to age dating. This is the principle of floral and faunal succession. We see in the geologic record that with time, organisms evolve and become more complex. That sequence of succession in evolutionary terms we call floral and faunal succession. So we can actually see certain animals or certain fossils in the record and correlate those to being of certain age or certain timelines. Okay, so that we know, we see a bunch of trilobites. Well, trilobites are older than, say, the dinosaurs. Okay, so we can put those into some degree of order using that succession idea. The other thing fossils are great for is correlation through time and space. We'll get into this more in historical geology if you guys continue into that. But we also correlate across time and space. Not all units are depositing at the same time all over the place. When we have a tectonic setting, we can have something that we call a transgression event. This is where, say, sea level is rising. And if you go to a seashore environment, and let's take a fairly typical seashore environment, you have the sandy beach area. Offshore of that, you have the fine-grained muddy area. Offshore of that, you have lime muds. Okay, the sandy area is going to create sandstone. The muddy area is going to create shale, and the lime mud is going to create limestone over time. We have all three units depositing at the exact same time in close vicinity. In a transgression event, the water levels are rising, and so that stuff is migrating inwards. And then we get to a regression event, which is where it will migrate back out. The deposition that's occurring of the units, we can have the same unit going through a large series of time and have many different fossils within it. So we use the fossils to correlate more for time in given locations. Okay, or we can also use fossils of the same type to say, okay, these rocks correspond to these rocks. A good example down here is the Mauve, I think it's the Mauve limestone and the Red Wall limestone in northern Arizona. Both of them are about the same age. In fact, actually, if you look at chunks of the two limestones, they look almost identical in terms of their physical makeup. But it's really the fossil makeup of them that shows that they're basically the same unit, just separated by hundreds of miles. Okay, so let's talk about fossils again just real quick. I know we touched on it briefly last week, but I just want to go over it again just very briefly. Fossils are basically the preservation of the remains or traces of past life. There are many different types. There are the body fossils, which are the actual hard parts. We can have them in a couple of different ways. We can have the entire animal's flesh, teeth, bone, because they were frozen, freeze-dried, preserved in tar sometimes, weirdly, or amber is another one. We can have remains that are petrified, i.e. they're turned to stone. We can have what are called mold and cast, very common for for many forms of sea life, where the sediments packed in around it, the organism decayed away, even the shell decayed away, leaving a mold, and then something filled it in, and that became a cast. We have carbonization, as I mentioned, where something can become carbonized, just a film of carbon. And then we have the others, the things that are not the actual bodies, like the tracks, the burrows, the feeding traces, gastroliths, which are very common with certain dinosaurs. It's one of the ways we know dinosaurs and birds are related. Birds have what we call a gizzard. It's sort of like a forechamber to the stomach, very muscular. They swallow rocks, and they use those rocks in that muscular gizzard to grind their food up. We find the same thing. We find piles of stones very similarly placed in certain dinosaurs that are polished. They're called gastroliths. We also can find coprolites or coprolites, basically dinosaur dung, or any sort of dung if you want. And generally, we need to form a fossil. We need rapid burial so we can preserve it, and then we have to, generally speaking, have to have hard parts. We can get soft parts in special conditions, but we generally have to have the hard parts. In terms of how correlation works with the fossils, it was a gentleman by the name of William Smith, who was an English surveyor and engineer. He was responsible for building of many of the canals in England. His wife was a collector of fossils. And Smith noted that you could correlate different rock units across England based on those fossils. And that really began a lot of that work back then. Now, let's talk about the physical continuity. Sometimes rocks will extend for very long distances and be the same units. Sometimes they don't. Sometimes it's hard to tell if you've had a lot of destruction that's happened and no fossils. So you've got a lot of folding and faulting. Maybe there are big chunks in between two locations. It can be very hard to tell if fossils are this or rocks are the same units if you don't have those fossils. Sometimes we base it on similarity of rock types. Now, in some cases, chemistry can actually play a role. A big one for us is igneous chemistry. And the reason for this is, generally speaking, every magma body is going to have its own chemical signature. Because of this, we can actually identify certain rocks as coming from the same source. For example, there are basalts that can be found in South America and Central Africa. When compared chemically, the basalts are identical. the odds of two different volcanic vents thousands of miles apart producing chemically identical magmas is astronomical. And the fact that the chemistry is the same is one of the clues that we have to plate tectonics. So we can look at this. Now, in terms of correlation by fossils, page 189A in your, or page 189 in your book has a really nice figure on this, 18.8, where what they do is they show you kind of a timeline. So what's happening here is this is showing you where fossils are found in terms of the geologic time scale. Okay, so, and it gives you what we would normally call the range of the fossils. So this fossil goes from here to here, this one goes from here to here. Now they have this unit here that shows all the possible different units that we see and where the fossils are at. And then this is showing, okay, here is the case where this unit and this unit are the same, this unit and this unit are the same. And that's also indicating that we have missing time in between. So we can use the correlations with fossils to do this. Now, sometimes what we're looking for in this is what we call an index fossil. An index fossil is a fossil organism that is very widespread geographically, but has a very narrow window of time that it existed in. And so anything that's like that makes a great index fossil because you can quickly identify something as being in a very narrow window of time if that fossil is present. The other thing that you can do, which is kind of what you can see here, is you can do what we call a cross correlation. So if I have something, and let's say I have these three fossils in there, okay, these three right here, just above my finger, that limits me to a specific range of time because there's only a certain point in time, a certain amount of time where all three were present at the same time. And so that can actually help me index my rocks to a degree and pick out the time frame for it. Okay. Now, the geologic time scale, which is shown basically on page 199 in your book, right here, was completely, totally, and utterly put together by nothing but relative age dating. That's all that built it. It was completely created without any actual numbers or dates. But in the early 20th century, we began to figure out that we could use this phenomenon of radioactivity to help us identify how old something is. Now, basically, what this comes down to is what we call a half-life. We don't really understand why it works, but basically, the long and short of it, the bare bones short of it is that if I have a substance, a block, okay, let's just imagine I have a cube. And let's say that cube is made out of some radioactive material. And to make this simple, let's say that radioactive material has a half-life of 30 minutes, okay? When that half-life happens, that 30 minutes, let's stop the clock, stop time, half the atoms in that material have decomposed through radiation to become what we call a daughter material. So the parent material is the radioactive material, the daughter material is the subsequent material. So half of it became something else. If I take another 30 minutes, half of what's left became that something else. I take another 30 minutes, half again. This is something we don't quite understand yet with physics, but every time there's a half-life, it's essentially half the material decays. If you can figure out why, great. There's a Nobel Prize in it for you. So what we're dealing with is when we're doing when we deal the numerical dating, the absolute dating, is we're dealing with radioactive isotopes. So let's review that again. Remember, the atom is composed of a nucleus surrounded by a cloud of electrons. The nucleus is what matters in this case. The nucleus is made up of neutrons and protons, and it's the number of protons that describe what the atomic number is of the element, and it controls all the physical and chemical properties of that element. The number of neutrons control what the isotope is, what version of it is, if you will. But certain numbers of neutrons in the nucleus makes a nuclei unstable, makes it unhappy, and it's going to break down. It's going to undergo some sort of change. And that change is what we call radioactivity. So there's a couple of different types of radioactive decay that we have to be worried about. Two decay, one, I don't want to call it decay, but the book does. The first of these is what we call alpha decay. So in alpha decay, a nucleus is sitting there and it fires off a small bit that we call an alpha particle. Well, what's an alpha particle? An alpha particle happens to be basically what we consider to be a helium particle, or a helium nucleus. It's 2 protons and 2 neutrons. This means that the atomic number of the material goes down by 2, and the atomic mass goes down by 4. So this is the one that does the most change in the atom. So the atomic number goes down by 2. Uranium, generally the first decay uranium goes through is a alpha decay, and the uranium turns into thorium. Okay. Another form of decay is what we call a beta decay. A beta particle is emitted from the nucleus. A beta particle is basically an electron. So in a beta decay, what's basically happening is a neutron is firing off a proton. A neutron is firing off an electron to become a proton. So what happens is the atomic mass number stays the same, but the atomic number increases by 1. Now there is an opposite to beta decay, which is we call electron capture. Electron capture usually happens when you have high energy electrons coming in from outer space. We usually refer to these as cosmic particles or cosmic rays, and it hits the nucleus of an atom, and the electron gets absorbed by one of the protons and turns that proton into a neutron. So basically the atomic number lowers by 1 and the atomic mass number stays the same. Now if you were to look at it as they show on page 194 in the book, they actually go through the entire decay series for uranium-238 to lead-206. This takes quite a lot of time. To be exact, it takes about 4.5 billion years for a half-life to occur. So right now, about half of the uranium that's ever existed on the Earth is gone. It's decayed away. Okay. Now we can do math with this, and we'll do this in the lab when we get to the lab on Geologic Time. I might hold off on assigning that until maybe the week of the midterm, and give you guys spring break to work on it. I know I'm nice, right? We can actually do some math on this and actually calculate things. But basically some key takeaways is to remember that every whole half-life is going to result in 50% less material. So we go 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, so forth and so on. In the sequence, it turns out there is a limit. And the limit is more or less about 10. Generally speaking, out beyond 10 half-lives, we're getting into the area where it's very difficult for our equipment to actually detect things. So, generally speaking, if we look at the half-life of any decay series, and those are given at the bottom of page 194. For example, potassium-40 decays over 1.3 billion years to argon-40. Uranium-238, 4.5 billion years to become lead-206. Uranium-235 takes about 703 million years to decay to lead-208. Rubidium-87 takes about 49 billion years to decay into strontium-87. The one that's actually maybe one that you've heard of before, carbon-14. Carbon-14 takes about 5,730 years to decay back to nitrogen-14. In fact, you're radioactive. You have a certain percentage of the carbon in your body is carbon-14 because carbon-14 is manufactured in the air by cosmic particles striking nitrogen, and there's a certain percentage of it that's in your body, and as long as you're alive, that percentage will not change. Now, how reliable is radiometric dating? Well, it can be fairly reliable, and it can be fairly unreliable. And this is because we have sources of errors. The error that we can get in radiometric decay is simply anything that keeps the system open or makes the system open. So when we're doing a radiometric sample, we want ideally a closed sample. We don't want to be sampling from near the surface of the rock where it's been weathered, where fluids have been active. We don't necessarily want to look at metamorphic rocks or other rocks that have been highly heated and shown evidence of heating or of hot water running through them because stuff could have been brought in. To give an example of this, you may or may not know about the Shroud of Turin. If you don't, that's okay. If you do, that's fine too. The Shroud of Turin is purported to be the burial cloth that Jesus Christ was buried in. It has an imprint on it, some people say, a photo negative almost, of a man with wounds. The authenticity of the shroud has been in question for quite some time, mainly because, one, that style of weaving is not known from the Middle East during the time of Christ. It actually didn't appear for about 300 years. And its history is a little iffy. When they did carbon testing on the shroud back in the 80s, they came up with some variable dates. The best dates still ended up saying that the shroud was probably, the material the shroud is made of, probably was created somewhere around 400 AD. But now there are problems with that. The shroud was hanging for a long time in a cathedral. At one point, that cathedral burnt down, and so the shroud actually has fire damage. It has soot on it. Well, that soot, that fire damage, can introduce new carbon, which can change the carbon makeup and cause us to have an error. Okay, so this is where we need ideally a closed system. We need to know that nothing is getting into or out of that material, so that we can get a good date. If we can get a good closed system, then our dating is going to only be as good as the sensitivity of our materials. How few particles can we actually measure? What's the smallest plus or minus on there? So generally when you see a study that gives a date, it's going to be plus or minus some point of time. So it could be 64 million years plus or minus 1.23 million years, something like that. And that's just that plus or minus is represented as the error in the system. Now, what we have done with radiometric time is it has confirmed the immensity of geologic time, simply because when we look at it, the oldest materials that we have found come from outside the Earth, namely the Moon and some asteroids. in meteorites, and we have found that the oldest material we can find in the solar system is roughly 4.56 billion years old. So that gives us the starting point for when the solar system had to at least start coalescing. So how old is the Earth? Well, interestingly enough, this has been a hotly debated topic for a few hundred years. In 1625, Archbishop James Ussher calculated, using the Bible, that the Earth was the Earth was created on 4004 BC. Particularly, if I remember correctly, it was September 19th at 4:30 p.m. How he got there, even I'm not quite sure. I understand his methodology of looking at the genealogy of the Bible, and so lived for so long, had this son who lived for so long, and so forth and so on. But to get down to a specific date and time, something's not quite right there. But, that was the first attempt. And, of course, it was using the biblical ideas. From a scientific standpoint, though, there have been a number of things that have been done to try to date the age of the Earth. Some scientists tried to say, okay, well, maybe the sun was the sun spit out the Earth, and we were a molten piece of the sun, and then it cooled down. Well, how long would it take to go from what the temperature of the sun appears to be to, if we took a ball of iron, because we know there's a lot of iron in the Earth, make a ball of iron the size of the Earth, start out near the temperature of what we thought the temperature of the sun was, and melt it, and cool it down. How old would that be? And somebody came up with, anywhere from 25 million years to 50 to 100 million years. Some people tried using salt. Think of it this way. Ocean water is salty, right? Not good to drink, but it's salty. River water is not salty. How did the oceans get salty? Well, the oceans got salty because the salt is actually in the river water. The rivers flow into the ocean, but the oceans evaporate. And that evaporation leaves the salt behind. Think back to when you lost a tooth. Okay? Besides the money the tooth fairy gave you, what did your parents give you when you lost a tooth? Well, if it happened at home, odds are you were given hot salt water to rinse your mouth out with to help cauterize the wound and stop the wound from bleeding. Invariably, you might have at one point taken the cup of hot salt water, sat it down in the bathroom, and forgot about it. And a day or two later, there's the cup. You look in it. There's no water left, but there's a ring of salt. That's because the salt is not taken when the water evaporates. Hence, when we talked to sedimentary rocks, it was one of the evaporite rocks. So if you calculate the salinity of the seawater that's going, or the river water going into the ocean, calculate the salinity of the existing seawater, calculate what the average evaporation rate is in the oceans, you could then work out a approximate time for how long the Earth has been around. And if I remember correctly, I think that one worked out around 100 million years, give or take. That was not bad, but not accurate because, well, not all the salt stays in the ocean. We do get pieces of the ocean that dry out, become part of the mainland bodies, and that takes the salt out of the ocean. So we've gone through a number of different things over the centuries trying to figure out how old the Earth is. But it's the radiometric age date, and it gives us our best date at roughly 4.56 billion years. Now, beyond this, going back to it, just to kind of briefly talk about it, the geologic time scale. We have since been able to add dates to the geologic time scale. So now if you were to look at page 199 in your book, you see actual numbers in there. And those numbers represent millions of years. So it tells you how long ago the breaks in the clock in the time scale were. So in this version, and there, it changes from different publications to different publications. So if you look at this one, page 199 in your book, and look at the chart that's in the back of the classroom, you're going to notice some slight differences. But the end of the Cretaceous was about 66 million years ago, 65 million years ago, 64 million years ago, somewhere in that ballpark. The Cambrian started about 540 million years ago, so forth and so on. But the way this is created, and again, was from relative age dating. Now, when we look at this chart, we notice that it's categorized. It's broken up into different units. So, for example, we have, starting on the left side, the eons. The eons are the largest expanses of time available to us in there. Right now we have a couple of different ones, and this is changing a little bit, so this is kind of fluid, but I'll give it to you. It used to be just two expanses. You had the Phanerozoic and the Precambrian, and the Precambrian was the vast majority of life, of the time on the Earth. Well, we're getting better at being able to read some of the older rocks, as well as reading the moon. And so we have broken up the overarching eon of the Precambrian into three other eons. The Hadean, which has no geologic history on the Earth that we can find. This is basically based almost entirely on the geology of the moon, because nothing is left from this period of time on Earth. The Archaean, which has to do with the development and the spread of archaea bacteria, which are some of the more primitive forms of bacteria on the planet. The Proterozoic, which is about the more common forms of life on the planet that basically have our type of cell structure. And those now make up what used to be the Precambrian. Now, in the Phanerozoic, we split it down to eras. And we have three primary eras right now: the Paleozoic, the Mesozoic, and the Cenozoic. Now, if I gave you a clue, you could probably figure out what those mean. Zoic means life. So paleo, right, ancient life or old life. Meso, middle life. Cena, recent or recent life. And then each one of the eras are broken up into periods. Now, each of the periods has its own symbol, and the book does a pretty good job of showing it here. It's also in your lab book, but each of the eras come out, and you notice that they go from the Cambrian to the Ordovician, the Silurian, the Devonian, Mississippian, Pennsylvanian, and with a note that they're also referred to as the Carboniferous, the Pennsylvanian and the Mississippian, and this is due to a difference between Europe and North America. Then we have the Permian, the Triassic, the Jurassic, the Cenozoic, then the Paleogene, the Neogene, and the Quaternary. And then the periods, at least for the most part, the periods in the Cenozoic, and to a lesser degree there are sub-breakups. The periods in the Mesozoic and the Phanerozoic are broken up as well. But most of the good work on this is in the Cenozoic, are broken up into what we call epochs. And so you have the Paleocene, the Eocene, the Oligocene, the Miocene, the Pliocene, the Pleistocene, the Holocene. And this one does not actually, there's a new one that's being proposed. I don't know if it's really taken hold yet or not. But it basically gives us a good foothold for understanding and being able to put things about the Earth's history into perspective. And all of it is built through these series of observations initially about what came first. Now, when we do the lab, you're going to have one of these exercises to do. We will do a simple one as a demonstration in class before you start on it. Then you'll actually do the one for the lab yourself. With that, the difficulty in putting these dates in here is you have to have datable material. Usually we use volcanics for that. So if you get a fossil site that's bracketed by some volcanic ash or lava flows, we can use those lava flows to give us a good, reliable date for that event, for those events, and then therefore get the actual age for the fossils done. But with that, I'm going to wrap it up here. As always, this is the video lecture. I hope you guys are getting something out of this. Please, if there are any questions, please send them to me, post them in the class forum, however you want to do it, and I'll talk to you guys later. Have a good one.